Well, hello guys. We're going to have a look at areas of regions now, and this is the first of the applications of integration modules which we'll be doing, following on from the core work of being able to anti-differentiate in and of itself. Okay, so let's go and have a look at this. It's very interesting. Now, in our quest to find the exact area under a curve, one way that we can do this is basically to draw rectangles across the width within which we want to find the area, the width being from A to B in this case, okay? And I'll show you some. There's some rectangles, and we could just work out individually the areas of those rectangles and add them all up. It would be a bit crude because there's lots of little loose ends. That's an underestimate there, that's an overestimate there, an overestimate there, and an underestimate there, isn't it? So, you know, it's a pretty rough and ready kind of way of doing it, but it is a start as a measure of a method of trying to work out the area under this curve. There's all sorts of things you can do, counting squares, etc., etc., but this rectangles idea, I want to pursue this and make it a little bit more refined. It's inaccurate because of the non-counted spaces and the over-counted bits, so those green bits are examples of underestimates, and the red bits there, which I've just coloured in, are examples of overestimates, okay? So it's a bit rough. And that is that there is the width of the rectangles which I've chosen. I've chosen in this instance, okay, arbitrarily chosen. So I've got 6 rectangles there, and I'd have to work out the area of each individual one, which would be the width delta x, meaning a small change in x, by the individual y values. And in this case, I'm doing just by the way the left-hand side is the side of the rectangle which I choose to touch the actual curve itself. So it's kind of like a left-hand side estimate of the area using those rectangles. Okay, so now what I want to say there is that the area therefore is approximately, and in this case it's very approximately, the sum. This is a Greek capital sigma, okay, which denotes in maths the sum. The sum of the heights, which is f of x, in this case it's the left-hand side of the rectangle's height, where it intersects the curve, times the delta x's, which are the widths of the rectangle. So it's the sum of all those individual rectangles' heights times their widths, added all up, between x's a and x's b. That's my estimate, or really a guesstimate, if you like, of the area. Okay, it is the sum of the areas of rectangles. That's very important that you get that notion into your minds, because that's what the whole thing of integration is all about. Now, if I wanted to make that whole process a bit more accurate, what I would do, guys and gals, is I'd choose thinner rectangles with less width, like these ones. And in so doing, I create more work for myself, because I've got so many more rectangles to work out the areas of. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 there instead of 6. Okay, so there's more work, but it's more accurate. So this is the trade-off. Life is full of compromise, and that's the compromise. You get a more accurate result because there's less loose ends and overestimates and underestimates up here, but you have to work out more areas basically to get that better result. Okay? Yeah, and the delta x there is much less than the delta x over here, okay? The width. So to increase the accuracy of the estimate, we can decrease their width and hence decrease the wasted space or the overestimated bits here as well, and get a generally more accurate result. Now, if we extend this idea that we've got here and take it to its limit, if we could then make less and less and less widths rectangles, thinner and thinner and thinner rectangles, making more and more and more and more of them, we would lessen all of this inaccuracy up here at this top end here. And if we could make them infinitely thin, if that was possible, we would actually come up with the actual area under that curve, right? If we could do that, and this whole notion is where we're getting to with the integral. So I can say that the area itself, the not estimate anymore, the actual area, is the limit of the sum of the areas of all these rectangles, their heights being f of x, the y value, their widths being delta x, the width value, the sum of all the rectangles in the space between A and B, and it is the limit as delta x, or the width, approaches 0, right? That is the actual area. And that is, that is the antiderivative of f of x, and see how the delta x over here morphs into a little dx, okay? So this thing in red here is actually that same thing in black, but it is the actual area under the curve. It's the sum of infinitely thin rectangles where their heights are the y value, or f of x, their widths are the x value, or the width, or delta x morphed into dx, between A and B, okay? That is the geometric significance of a definite integral, okay? It is the area. It's actually the signed area, S-I-G-N-E-D, the signed area under the curve, as we'll go into and explain in a moment, okay? So, it is, yes, that thing, that funny looking thing there is actually a stretched out, pulled upwards and downwards, stretched, elongated, vertically, lazy S, standing for the sum. And I want you always to remember that. It stands for the sum of the areas of those rectangles. And the use of that S for sum notation is called the Leibniz notation, after a mathematician of that name who used it some hundreds of years ago. There you are. Now that is the geometric significance of what a definite integral is. It is actually the signed area under a curve. Okay, now let's just explore that a little bit more. Yes, it is very exciting. It is very exciting. So let's just take it and play with it a bit more so we can see how to deal with it. The area under the curve, yes, the area, well, it's actually the signed area under the curve, but it is an area under the curve, is the integral, or the antiderivative, they mean the same thing, of f of x with respect to x, or, you know, the heights times the widths, right, between A and B. That's what it is. Yes, and it's equal to the antiderivative function evaluated at B minus the antiderivative function evaluated at A. In other words, substituting B in instead of x, and then subtracting the thing with A substituted in for x, okay? Yeah, where the antiderivative function is just the integral of f of x with respect to x, okay? NB, now NB, always, please, please, please always think of definite integrals, which are the same as definite antiderivatives, as the sums of areas of rectangles. Because if you do that, and never lose sight of that, never lose the basics, you will know how to deal with these things. Otherwise, you can very easily get mucked up. Now, what have we got over here? Now, this is where I go into the fact that integrals are actually, they're not just areas, they're signed areas. They have a plus or a minus associated with them. So in that sense, they're not pure areas, they're signed areas, as I'll explain as we deal with this graphic here, okay? Now, each rectangle, there's an example of a rectangle which, this rectangle, and with its brothers and sisters which span across this width from A to B, would make up the estimate of the area. Okay, this rectangle here, just for illustrative purposes, I want to explain to you that basically it has both a signed width, and a signed height, right? That is, the width and the height are both either positive or negative, and therefore the definite integrals will either be positive or negative, right? That's extremely important that you get that. The sign and the magnitude of the widths and the heights is found by treating them each as directed line segments or distances relative to their starting point. Now, that's an absolute clincher that statement there. We'll deal with it as we go over the page, and I'll explain it a little bit more. So that's what we were saying before. Now let's look at the widths of this particular example here. Okay, the width, right. A is the starting point for x. A is the starting point for the widths, right? And we are moving towards B as the finishing point for x, okay? So hence every width interval of every blue rectangle here, which would span across this whole space from A to B, they basically start from the left. They start from the left and they move to the right, just the same as the sequence from A moving across to B. So does every rectangle have the same sequence of starting here, finishing here, okay? So they move from the left to the right, which is a positive distance. As if you think of it on a number line kind of situation, it would be a positive distance. For example, think of any number line. If you moved from, say, 2 to 5, then the distance that you move in a directed line sense is 5 minus 2, which is plus 3. That's what I mean. But if on the other hand you move from 5 to 2, well then the distance that you moved in a directed line meaning is basically 2 minus 5, which is minus 3. You get it? So if you move from left to right, you get a positive distance. If you move from right to left, you get a negative distance, okay? Yes, that is a positive distance, right? Now, as far regarding this example here again, if we're looking at the heights of these rectangles, the blue rectangle is an example of which the heights are taken relative to their starting point. And in this case, the starting point is the x-axis, or where y equals 0. So in this example, those heights of the blue rectangles will be also positive, as I've shown you here. Therefore, each signed area of each blue rectangle, if you like, is going to be a positive width times a positive height, which gets you a positive signed area as a result. Therefore, in this case, f of x with respect to x, the antiderivative of f of x with respect to x from A moving to B, A is the starting point, B is the finishing point, in this example is going to be positive, okay? However, guys, if you move from B, the lower terminal being the starting point, to A, the upper terminal being the finishing point, okay, the integral of f of x dx taken in that direction from right to left, moving in the x direction right to left, it would be negative, because you would be multiplying a negative width by a positive height, and you would get negative, okay? Yes, that's because the width is in the direction from right to left, okay, which is a negative direction and distance. Now, here's the big revelation here. I want to explain this to you. The area, the so-called area, if someone's talking about the area under a curve, a question asks you for the area under a curve, this basically refers to not the integral, not the signed area, but the unsigned area. Just the number, just the width times the height, without any reference to pluses or minuses at all. That's what the area means. So therefore, it is the absolute value of the signed area, because the signed area can be plus or minus, right? That is, it is the area without the sign. Da-da-da-da, that's really important, okay? So the area is actually the modulus, or the absolute value of the integral of f of x with respect to x from A to B. And in fact, it can be plus or minus the actual integral, because the area always has to be, if you like, it can't be negative. So in that sense, it's always got to be positive, if you like. And so therefore it can be plus the integral if the integral is positive, or it'll have to be minus the integral if the integral in and of itself is negative. Minus a negative getting you a positive answer. In other words, the area, it makes no sense to call an area negative. So that's what you've got to do to the integral to make sure the area comes out plus, if you like. Yes, do you get me? Yes, areas are unsigned areas and integrals are signed areas. That's the difference. So you've got to make sure the area always comes out plus, because it can't be negative. That's the big thing you've got to understand. Now I'll give you an example of this. This is a really neat example, this one. We've got the graph of y equals x plus 1, running from x is minus 2 up to x is plus 2 up here, right? Now, the interesting thing to note is that part of this graph goes below the x-axis and part of it is above the x-axis, right? Now, that's a very important thing because it illustrates something extremely interesting. Now, we're taking the graph of y equals x plus 1. I'm going to explain the interesting bit now for you. Now, let A1 and A2 be the areas as shown, as you see there, A1 here, A2 there, alright? Now, using the formulas for the area of a triangle, because we can very easily geometrically work out what A2 and what A1 are just by height times base over 2, as that's the area of a triangle, right? We don't care about, in this case, whether that's plus or minus. We're just going to say A2, the actual area. A2 is base by height over 2, which is 1 times 1 over 2, which is a half, yeah? Same thing for A1, base times height over 2, which is 3 times 3 over 2, which is 9 over 2, or 4.5, alright? So the combined area there, the unsigned combined area of A1 plus A2 would have to be 4.5 plus a half, which is 5, okay? 5, you agree? That's the amount of real estate, just the amount of land, if you like. Alright. Now, the thing is, though, that signed areas cancel. Signed areas cancel, okay? So if I was to work out the integral of the function x plus 1 with respect to x from minus 2 to 2, in other words, spanning from here all the way over to there in one fell swoop, guys, what will happen is this negative part, that'll be a negative integral, and it'll be negative a half. This will be a positive integral, and it'll be positive 4.5, so that the net result of working out the integral in one operation from minus 2 up to plus 2, you won't get 4.5 plus a half being the actual unsigned area of 5. You will get 4.5 minus a half, which will come out to be 4. That's the deal, guys. So if they asked you for the area under this curve between minus 2 and plus 2, and you just worked out the integral, you'd be wrong because of this cancellation effect, this negative bit here, minus a half, and the positive 4.5 interacting just to get a net result of 4. Yes? Right. That's what I want you to get. If you are asked for the area, you have to work out this integral, strip it of any minus that it might have, work out this integral, strip it of any minus that it might have, and then add up just the two numbers to get the unsigned area. Okay? That's what you've got to do. I hope I'm explaining that right. Yes, that's 9 over 2 minus a half, you see? You getting it? I think you are. That's really good. Now, also, let's have a look at this now, just to really ram the point home for you, and so that you get it really clearly. We're going from minus 1 to minus 2. Now, in that instance, I'm going to do this little bit here, this A2 bit, but I'm doing the integral from minus 1 to minus 2. Now, that's a negative width. That's a negative width, and it's a negative height relative to the baseline, which is the x-axis. That's where y is calculated relative to where y is 0, which is the x-axis, and that'll be a negative height, a negative width. So negative times a negative it'll get you a positive integral of a half, right? It gets you a positive integral of a half when you're moving back this way. Okay, you see? Yeah. Okay. So the width is negative, the height is negative, multiply them together and you get a positive result, okay? So if you were asked for the area of A2, you could work it out as the integral going from minus 1 to minus 2 because you are sure of getting a positive result, okay? But you wouldn't work out the area as being the integral from minus 2 to minus 1 because that would get you a positive width times a negative height, which would get you a negative result, and that would be wrong. You'd have to say it would be minus the integral going from minus 2 to minus 1, and that would get you a minus times a minus, which get you a positive for that area, just the area, right? Are you getting me? You've got to think about this stuff. Now, what am I saying here? The integral from -2 to -1, that's going that away to the right, would be negative. Yes, it's -1/2, okay? Because you've got a positive width times a negative height, right? Multiplied together to give a negative. Yeah? Okay. Okay, I think you get it now. Sorry if I'm being boring, but I really want to get this point home to you so you don't make the mistake that a lot of students do with this sort of stuff. Now, the area, A2, is the modulus, or the absolute value of that integral, right? And it's equal to the negative of the integral going backwards from, wait a minute, from -2 to -1, I mean going forwards, from -2 to -1 going forwards in the x sense, you get a negative integral, so negative of the integral will get you a positive area, like a positive result, which coincides with the area, the unsigned area, and it would be plus the integral from going backwards, if you like, from -1 to the left to -2. Okay, because that is a positive result anyway. Yeah, that's the deal. That's how you've got to do these areas. You've got to work out what the integral is going to be, whether it's going to be positive or negative, and then take the appropriate action, either by reversing the terminals or putting a negative out the front of the integral to get a positive result. That's what you've got to do. Okay, I think I've explained that reasonably well for you. Now let's do some examples. We've got a graph of that thing. We have to work out the area. The area, which means the unsigned area. If they just ask you for area, they're talking about the unsigned area of the shaded region. Now, it's that, right? Now, we've got a width going. We're going from left to right in this instance, aren't we? From -1 to +1. That's the way I think we should do it. And what will that give us? A width, a positive width, and a positive height? Yes, so we're going to get a positive integral, so the integral in that sense will coincide with the area. Yeah, there it is. Look over there, have a look. We've got a positive width, we've got a positive height, so we're going to get a positive integral. So therefore, you know what to do now. You're not getting it wrong, so you just go ahead and do it now, and you get that. And evaluating that, we're going to get that, and we're going to get that. Pi on 3 is the integral, which is also the same as the area. Okay. Very good. Next one. This is a graph of 6 over 4 plus x squared. Now, we're asked for the area again, right? So we need a positive integral then, okay? So if we go from -2 to +2, we've got a positive width, a positive height, and therefore a positive integral. Look over there, check it out. So yes, positive width, positive height, and positive integral. So everything's good, so we can proceed, because the integral will coincide with the area without any manipulation on our part to cause that to happen by reversing terminals or putting some sign change out the front. So you just go through now and just evaluate it. So that's a tan beastie, isn't it? Yeah, so you need a 2 there, so you put a 2 down here to compensate. You put the 6 outside, you don't need to integrate the constants. So what you get there is 3 times inverse tan of x over 2. Evaluated between -2 and +2, and just going through and doing it, you get that. We're going to get that. 3 pi on 2. Yeah, 3 pi on 2 is the integral, which also coincides with the area. Alright, you're getting this now, aren't you? Great. Now, what's this thing? Oh, well, they want us to sketch the graph, which I'm not going to be bothered sketching the graph. I'll show you the graph. I just want to illustrate the point of all this areas of region stuff for you so that you really get this. So there's the graph. We have to evaluate, what do we have to evaluate? The area of this region here. Okay, that's fine. Now, we need that. You're between 0 and 1/2. Yeah, this is 0, x is 0, this is 1/2. Now, okay, we have to do the analysis thing to work out whether the integral is going to come out as positive, because they've asked us for an area, which must be positive. Now, yes, how do you do that? How do you do that? I don't know how to do that. Do you? Well, we certainly haven't been taught how to do that. So, basically, having worked out, guys, that this will be a positive integral, because the widths are positive, the height's positive, so the integral is going to be fine. But the problem is we can't do the jolly thing because we don't know how. Well, actually, I do know how. I'm going to show you, but it's a different technique, which is I want you to have a very close look at because it's really useful. And this is when you get something like this that you just can't do, you morph into this technique that I'm about to show you, and which will dazzle you. It's so clever. Okay, I didn't think of it, by the way, but it is very clever. Now, can't do that. No, we can't. So what we do is we think of this as A1. We think of that as A2. We've got to work out A1, which we can't do. But actually, ladies and gentlemen, we can work out A2 by some mathematical skullduggery, which I'll show you in a minute. So what we do is we work out the whole rectangular area, this one here, which I'm just going around the perimeter of with my little green hand here, as, okay, the height is pi on 2, the width is, down here, is a half. So the area of that rectangle, which is made up of A1 and A2, would be a half times pi on 2, right? Which would be pi on 4. Now, what we're going to do is we're going to work out A2 and then take that away from this total to get A1. Now, you might ask, what on earth are you going to do that for? Well, the reason is that A2 is relatively easy to work out, whereas A1 is really hard. We don't know how to do it because it's, you know, this looks murky. We can't do that. Now, but we do some very interesting mathematical tricks here to work out the integral in here, which will be a positive integral. Now, watch this. We can work out A2 as follows, right? So let y, we know that we're trying to do this. So we let y equal this thing, right? Now, I'm going to make x the subject. You watch this. Therefore, sine y, if you imagine taking the sine of both sides, if you like, if you think of it that way, you could say that sine of y would be 2x. Yes, because y is the angle whose sine is 2x. So therefore, sine of that angle equals 2x, if you get my meaning. Now I'm going to make x the subject. Therefore, x is a half sine y. Therefore, now, look. This is very extraordinary. What have I done? No, I haven't gone insane. Well, some might say that I have, but not in this particular context, I haven't. Now, what am I doing? I'm going to do some horizontal rectangles with heights of delta y, between y is 0 and y is pi on 2. Now, why, oh why am I doing this to y? Well, I'll show you. Look, seeing the diagram, I'll show you what I'm going to do. Because it's easy to integrate, that's why. I'll show you. Look, see, I'm going to do rectangles with heights, or if you like, horizontally out, and the heights are actually x values, where they hit the curve. That's the x value. And then the widths are going to be delta y's. Okay, right. Now, watch this. All of these, right, I'm going to do that, right? Now, stand by, fasten your seatbelt, look. Because x equals sine y, integrated with respect to y, between 0 and pi on 2, and there's the half bit there, from there up there, right? Now, you see, sine y is very easy to integrate with respect to y, because it's just going to be basically minus cos y. So therefore, it's really, really, really easy to work out. Okay? There it is. It's a half of a minus cos y evaluated between 0 and pi on 2. And there it is there. There it is there. Now, come on, step further. Yeah, so cos of pi on 2 is nothing. So therefore it's just, and cos of 0 is 1, so it's just going to be a half. That's what it is. So A2, ladies and gentlemen, guys and gals, is a half. Is a half. So now, you see we're nearly there now, look. So if A1 plus A2 equals this thing which I worked out up here, pi on 4, and we know now that A2 is a half, I can work out A1 by difference. I know. It's marvellous. So, there it goes. Look. That is my answer. Now, you need to be aware, if they give you some ridiculous looking thing that you can't do, like this, and sometimes it can happen with trig things, sometimes it happens with loggy things too. Okay? Yes, it can. So that's where you be on the lookout for this particular technique, where you can work out the overall area of some rectangular thing, and then you can basically do the area that they don't want and subtract that from the whole rectangle to get the area they do want by using rectangles on their sides, horizontal ones where you do the integral of x dy, okay? Yes, I know. Wonders never cease and our education continues. So, let's keep going. We're going to run out of time here. The video is going to be too long. So, sketch the graph of blah blah, and I'm not going to sketch the graph, I'm just going to show you the graph. Right, between -1 and 1. Okay, now, our integral analysis, this is what we want. Yes, we've got positive widths and we've got positive heights, so the integral is going to be positive, so no problem. They're asking us for the area, so the integral will be positive, so it coincides with the area. Yes? Okay, so there we go. We're looking for that. Now, what does that look like? Partial fractions, I think. Yes, 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 yes. So let's hurry up and do that. We get that, and we analyse it, and we get that, and we pick our strategic values of x, and we get A and B very fast. You can pause the video and have a look if you like, just to check that I'm right. There it goes. Yes. Now, alright guys, what we want now is we want the area, the integral, which is the area, and there it is, made in a form, the partial fraction form, which we can actually do. Alright, I've left the quarter out here. Right, so that's going to be the log or minus the log of the modulus of 2 minus x, and the other one's just going to be just the log of the modulus of 2 plus x. There it is, right? Now it's just a matter of evaluating it, and you get all that stuff, and that's naught, and so is that. Log of 1 is always naught, so that's what we get. That's what we get, guys. Yes, and if you like, you can put it like that, yeah, by using the log laws to put that half as an exponent, 3 to the half, which is root 3. Okay, you're right. I think there's one more now. This is one that we have got to do now because, yes, because the integral is going to work out to be negative, I think. So we want the area of the shaded region. So let's do that now. Our analysis shows us that we've got a negative height and a positive width. So that's going to get us a negative integral. So therefore, if we want the area, we better do the negative of that integral to make it positive, because the integral in and of itself is negative, right? Okay, so now you know what to do, right? If you didn't want to put the negative out the front, you would just reverse these terminals, where that would be 3 pi over 2, and that would be just pi over 2, right? And that would also suffice. It would get the same result. So now all we've got to do is know how to integrate that. That's an odd trig function. So the technique, you use the odd trig technique, where you take one of those causes out, put it over there for the dx, and you make sine equal to u. There it goes, and you go through all that, and therefore you change your terminals, which you have to do. If x is pi on 2, you would be 1. If x is 3 pi on 2, you would be minus 1. Now we're ready to go now with u. Mr. u, come on down. So we've got this minus, now that's cos squared, which is 1 minus sine squared, right? That cos squared is 1 minus sine squared, which means we've got 1 minus u squared, and the cos x dx is just the du term. We've got the minus out the front. Now, if you like, we can reverse these terminals. Yes, that's right. It just makes it a bit more logical and easy to figure out what you're doing when you put the lesser value at the start, at the lower terminal, right? Okay, now it's easy now. Easy to do. That's going to be u minus a third of u cubed between minus 1 and 1, and we just evaluate away, and we get all this stuff, and therefore we get 4 over 3. That's the answer. That's the answer, guys. Okay, how did you go? How did you go? Don't you know? It's great fun. So have a good lot of practice, and we'll see you at the next exciting instalment. Okay, and bye for now.